So my name is Doug Keller. I am the technical lead for our pipe products in the Americas. LyondellBasell, or LYB, is a leading manufacturer of polyethylene and high-density polyethylene for pressure piping applications.
Yeah, and you guys are very active and big supporters of the Alliance, and you guys certainly believe in education. So with that, Doug Keller, take it away. Thank you for being here.
All right, thank you, Peter. So just a little bit of background for anybody who's coming new into high-density polyethylene. So polyethylene is a polymer, and it's made up of ethylene monomer units. To the right, you can see what an ethylene looks like. It's two carbons, which are black, with two hydrogens, the green, attached to it. And the two carbons are actually double bonded to each other, and that's what we call ethylene. We then take the ethylene monomer material and we polymerize it together, where we open up the double bonds between two ethylenes and they connect together. So this is very similar to a metal chain, if you want to think of it that way, which each individual link of that metal chain being an ethylene monomer in the case of polyethylene. So that's how we make polyethylene, is by stitching those ethylenes together. Polyethylene is a semi-crystalline thermoplastic material. By semi-crystalline, we mean that it has both a crystal or an ordered structure and an amorphous portion, which would be a disordered structure to it. In addition, it is a thermoplastic, which means that it can be heated repeatedly without damaging the material, so that we're able to both form it into a pipe or into a fitting, and then fuse those a pipe to a pipe or a pipe to a fitting using heat. So as a polyethylene manufacturer, what I control is the molecular weight of the material. So how many of those ethylene units I string together. The molecular weight distribution of the material is also something that I have control over as well. So we don't make chains of exactly the same length. We have varying lengths of the chains because it provides different properties for us. And then we can also adjust the density of the material by adding co-monomers. So those co-monomers are typically butene or hexene. And what they do is they go into the linear chain, which you can see in the middle. And then when I put a co-monomer in, which is down on the bottom right corner, what that co-monomer does is it disrupts the crystallinity, the crystal structure of the material, which allows for a lower density. So the more co-monomer I incorporate, the more I can change the density. So high-density polyethylene as a material is typically between 940 and 970 grams per cubic centimeter. Next slide. So over the years, polyethylene has evolved, and this is a good thing. Polyethylene can adapt and can be changed to the current needs of the material. So we start off with a PE 1404 material. If you have a lawn sprinkler system, or if you have installed a lawn sprinkler system, that black pipe that you can get at one of the big box hardware stores is a PE 1404 material. PE 2708 was the next evolution. This is what we call a medium density polyethylene. This would be yellow gas pipe. We then moved to high density polyethylene at PE 3608, and our current material for sale in the market on high density is a PE 4710 material. And over time, we've been able to increase the pressure handling capability of the material to adjust and to meet different market needs. Next slide, please. So when we talk about polyethylene, there's two different types of polyethylene for pressure pipe application. One is unimodal, the other is bimodal. Most of the polyethylene PE 4710 materials today are bimodal polyethylene, which means that we can tailor the material to meet the particular needs. So one of the issues in the past with polyethylene pipe has been slow crack growth resistance. And slow crack growth resistance is the common failure mode of polyethylene pipe in the absence of third-party damage. So what we've been able to do is take that co-monomer that I talked about and put it into the high molecular weight region of the polyethylene using the bimodal process. That allows us to get superior slow crack growth resistance, so that we've now pushed out failure by slow crack growth well into the future, probably well beyond the design life of the polyethylene pressure pipe system. Next slide. And if you click one more time, please, or a couple more times. Yep, that's good. Thank you. So the constraint with unimodal is that we're putting everything into the same pot. So if we think about this from a cooking analogy, everything is in the same pot, which means that we have a relationship between the pipe service life and the slow crack growth resistance, which is the black line in the first diagram. Because we have that particular property set up, the slow crack growth resistance is a function of the density, and that's something that we have to balance with the hydrostatic design stress, or the ability to handle pressure. The lower the density, the less ability to handle pressure. What polyethylene and bimodal does is it gives us that green line in the upper right-hand corner, which allows us to shift the relationship between slow crack growth resistance and density. That allows us to have a higher hydrostatic design stress and also a higher pipe service life because of the higher slow crack growth resistance. So it allows us to have the best of both worlds, high pressure resistance and high slow crack growth resistance. Next slide, please. So we offer several benefits in polyethylene pipe over other types of materials. There's a balance of stiffness and flexibility. This is very useful in regions with ground movement. Now, that ground movement can either be abrupt, like a seismic event, an earthquake event, or it can be freeze-thaw cycles, transitions between wet soil to dry soil, things like that. We also have excellent chemical and corrosion resistance. So if you're in a hot soil situation where that soil is eating through your ductile iron pipe or your cast iron pipe, polyethylene is impervious, is not bothered by the soil conditions. It's tough in abrasion resistance. You've got good impact resistance, and it's also fusible. And as I've said, we're able to advance that material, which is, again, is a good thing. We're able to address some of the concerns that are in the industry. One of them being improved chlorine or oxidative resistance. So chlorine disinfectants are typically used in water systems, in the secondary water system in the distribution, to keep the water clean until it gets to your tap. We've been able to deal with and address the issues that earlier generation polyethylenes had with oxidative resistance. And what we're going to talk about today is the improved sag or slump resistance. This allows us to make larger and larger diameter polyethylene pipe than we could make in the past. So that 48-inch and greater that we're talking about today is because of the low sag materials. Next slide.
So Doug, I have a question for you.
Yes, sir. Yes, sir.
The other materials tend not to focus on failure. Yet whenever I speak to you and other pipe guys, you know, the conversation always goes to failure mechanisms and slow crack growth and things like that. Why are you guys so focused on failure when everybody else wants to avoid it?
Well, because we can actually solve for it, Peter. So as opposed to wrapping your ductile iron pipe in a polyethylene bag or coating the inside with cement to deal with corrosion, we have a material that's corrosion resistant already.
Right.
As an engineer, I want to know about failure. And as a material designer and producer, I want to know about the failure because I can design away that failure. So you can put your head in the sand and ignore it, or you can be upfront about it and fix it. And that's what we do, is we fix those issues.
Well, and I also think that's related to the fact that we have solved for the typical failure mechanisms of other materials, yet we still recognize that we can fail too. And as you said, over time, as we've gone from first, second, third, and now fourth generation HDPE pipe resins, that every time we come up with a new one, we're solving for a different type of failure, or we're making it better. Is that correct? That's
correct, Peter. I mean, I think we all would agree that anything you put in Mother Nature, she's going to destroy at some point. Mountains turn into sand over time. I mean, everything gets broken down. We just need to address that and push it so far out that it's not a concern, and that it outperforms all of the legacy materials that are being used today. And that's what polyethylene does.
Yeah, for sure. Well said. Thank you very much.
All right. Thank you, Peter. Next slide. So very briefly about slow crack growth resistance. So what happens is if you get some type of a a load imparted upon the pipe, some type of a point load. Maybe it's put down on a rock. Maybe there's a deep scratch on the pipe. What will happen is with the internal pressure, you will start to open up a crack. So that crack is growing from the inside of the pipe, which is that vertical line represents the inside wall of the pipe. And what it does is it actually pulls apart the amorphous regions. So those blue rectangles are actually the crystal structure. And in between those crystals are polyethylene chains. And the way to think of them, simplest way, is Velcro. So the more chains that we can get, the more Velcro essentially between the crystal structures that we can develop, the harder it is to pull those crystals apart, which means that we have much greater slow crack growth resistance and therefore much longer pipe service life. But that crack will grow over time. We have not eliminated slow crack growth as a failure mode, but what we've done is made a material that is resistant enough that we are well beyond the design life and well beyond the 100 plus years of service life that we are expecting today from polyethylene pipe. Next slide. So this is just kind of a close-in view of a slow crack growth failure in a pent sample. The dark area in the right picture where we said the initial notch is we put a notch into the pipe, so we're already starting that failure mode. And then we apply a tension to the pipe at elevated temperatures or to the coupon of material. And so what we're able to see is that we are now pushing well into the future. Initial work on the pent test said that 1 hour of pent time is roughly 13 years of failure of lifetime in the ground in a typical environment. 4710 materials have to be greater than 500 years or 500 hours of pent. Is it linear to say that pent is, or a material with 500 hours of pent is 6,500 years plus in the ground? Probably not, but it is well out into the future such that it doesn't become a concern. And most of the 4710 materials today are 2,000 to 10,000 hours of pent. So really, if the pipe is properly installed, we do not think that slow crack growth is going to be an issue and will cause failure of the pipe well beyond its design service life. Next slide.
Doug, just to interject to what this really means to all the municipal water and wastewater audience out there, we do have an entire separate presentation on open cut, but we won't get into the weeds. Basically, a 6-inch, 8-inch HDPE can be installed with 3/4-inch particle size surrounding it for the entire duration of that pipe, and that happens to correspond with what's called a 57 stone, which shakes out of that 57 sieve, which is used to stabilize the bottom of the excavation. So the industry's advanced even farther beyond that, and a lot of that has to do with the testing rigors of being used for gas mains. Is that right, Doug?
That is correct. So the pen test really came about in looking at gas mains, and that's where the work initially was done because some materials produced in the 70s were showing premature failures in gas mains, and that's where the pen test was developed to replicate the type of failure mode that they were seeing in gas mains. And at the time, those materials were testing at about 1 hour of pent. And again, as I said, modern materials today, 4th generation materials, are in the 2,000 to 10,000 hour range. So why do we need low sag material? Well, if you're familiar with the way we pressure class polyethylene, for example, a DR11 is a continuous operating pressure of 200 PSI. And that DR is the average outer diameter of the pipe divided by the minimum wall thickness. So as long as that ratio is an 11 and you're running in a water environment at room temperature, your pressure class or your pressure rating for the material is 200 PSI, continuous operating pressure. As we go to larger and larger diameter pipe, with keeping that same ratio, keeping that same operating pressure of 200 PSI, we are now in the position where, for example, a 36-inch DR9 pipe in this case would have a minimum wall thickness of 4¼ inches. When we go to extrude that material, we heat the polyethylene up above its melting point, and then that pipe is extruded and it goes down through a set of cooling tanks. Well, it takes about 11 hours for a 4-inch wall or 4.25-inch wall pipe to cool down to the point that that material has solidified in the middle of the pipe, because it solidifies from the inside and the outside moving in. Next slide. So because of that several hour cooling time, what happens is you still have molten polyethylene in the middle of the pipe wall, and gravity is still pulling on that material, and it causes material to move from the top of the pipe to the bottom of the pipe, which means that the top of our pipe gets thinner, the bottom of our pipe gets fatter, and that's not what we want. ASTM F714, for example, on water pipe and large diameter pipe, says that as a pipe manufacturer, you can have a maximum thickness variation from min to max, that difference in wall thickness of 12%. Anything above 12% does not conform to the standard. Similarly, it would be the same for AWWAC 906. So that 12% thickness variation really limits our maximum wall thickness for a system, and that system being a material, a pipe dimension, and the extrusion setup. Next slide, please. So what we've been able to do is, again, address an issue with the industry, which was a maximum wall size that was possible. And we'll show a chart later on from F714 that kind of shows where beyond a certain dimension ratio sizes weren't available. We're now able to have a material that resists movement while in the molten phase to allow for a more uniform wall thickness. The importance here is that a pipe producer is buying polymer by the pound, but they're selling it by the foot. So the less material that they can put in, the more economical the pipe is to be sold. And for an installer of the pipe, it means that you have less variation in wall thickness. So you don't have to be concerned about finding Humpty Dumpty's low point on the pipe and aligning those all up together. So what we're able to see now is that we have less mismatch in wall thickness between sticks of pipe, and wall thicknesses greater than 7 inches are now possible for high density polyethylene pipe. And on the right, you see a picture that Rainer Ritz, who's a European producer, you can see how thick that pipe is. If we assume that gentleman's head is probably like 10 inches from his chin to the top, that's a pretty significantly thick pipe that is possible to be made. Next slide. So again, as we looked at earlier generation materials, if you look down on this picture and look at the bottom, which is the thickest part of the pipe, to the top, which is the thinnest part of the pipe, this was a standard PE 4710, standard in terms of its sag resistance. Nobody would want to buy pipe like that. It's, you know, it's just not good pipe. What we've been able to do, as you saw from the previous slide, is have a much more uniform wall thickness now because of the low sag materials, because of our ability to go 6 inches, 7 inches, 10 inches, depending on the dimensions of the pipe, to make these large diameters and larger wall thicknesses, so that we're able to effectively go after ductile iron and concrete in those very large diameter pipes. And I believe this is my last slide, Peter.
All right, count me in. So, you know, Doug's talking about the ability of the industry to manufacture pipe using fantastic resins in the larger diameters that meet ASTM standards. So the Water Research Foundation and EPA got together and they did an exhaustive 2-year study where they looked at, hey, we already know small diameter polyethylene is cool. What about large diameter? And you know what, guys? It's the same resin. It's the same pipe. The durability and the reliability of the product is evidenced in this study, proves that it's good to go. Alan Ambler, next slide, please. And, you know, Doug talked about pent. You know, I was like, what the heck does pent mean? Well, pent means it's this test that says our pipe's going to last a really multi-generations, well over 100 years. So the GTI out of Chicago has done some significant testing on polyethylene. They did this 2 million cycle test, and we take the pipe at full pressure and we surge it, we hit it with a surge, and the pipe tests new. But this has always been in the lab, this work that has been done. Well, we also have a study that's been done by the UKWIR, published in 2021. That's the United Kingdom's version of the Water Research Foundation. And first and second generation polyethylene pipe that had been in water service, in other words, in the presence of chlorine, tested new, and they anticipated those first and second generation resins, therefore pipes, would last over 160 years. So we have the lab data. We've got this new data that's now 3 years old coming out of UKWIR that tells us that what we're telling you is indeed accurate, is what we're finding in the field. Now I'd like to introduce my friend Matt Danish from Agru. Matt, would you please come on? And Matt's going to talk about, hey, Doug's got this great resin, as do other member companies, but how does and what does Matt Danish and Agru do with this resin when they get a hold of it in South Carolina? Welcome, Matt Danish.
Hey, how's it going? Okay, so yeah, once this resin was developed for this low sag, that allows us to make large diameter pipe in heavy wall thicknesses. So diameters up to 10.5 feet are possible now, with wall thicknesses up to 6 inches in thickness for solid wall extruded HDPE pipe. And the HDPE pipe that's produced in this manner is produced basically the same as your smaller diameter pipes. It's just larger in wall thickness due to this increase in the sag resistance of these PE 4710 resins. And as a result of we've been making this large diameter pipe now for about 7 years. It's been on the market, and some of the standards now have started to increase the sizes, like F714 now goes up to 3 meters in diameter, which is 118 inches. And so the specifications for F714 allow for these large diameters to be made under their standards. And the AWWA is still coming along with the diameters up to 65 inches. And so we're seeing the standards increase in their size range according to what can be produced out in the industry now. And internationally, it is being produced as well. And the ISO standards international are seeing these sizes up to 3.5 meters in diameter. And so one of the great things about HDPE pipe when it gets into the larger sizes is it behaves just like the smaller pipes. We were able to use it in the same manner as far as projects that require more flow. And so large diameter in the past, like they were saying, was 48 inches. And now we're producing pipe 128 inches in diameter. That's a little over 10.5 feet in diameter. And it becomes a little bit more difficult because the pipes are heavier because per linear foot. And so we're still able to put them on trucks and ship them all over the country, even if they are almost 11 feet in diameter. And basically they're welded the same way with butt fusion welding, and they have the same properties and also corrosion resistance, all the other great things about all the other pipes. And so this heavy wall pipe that we're able to produce then can be used in higher pressure applications for the smaller pipe, and then for the larger pipe it's used for situations where you have the need for very large water flows. If you have to encase canals for irrigation systems, you can use this very large HDPE because it's much better to go with a single pipe than if parallel pipes, because the diameter going larger in diameter actually gives you more flow per diameter. Since the Hazen-Williams formula, if you basically take that formula that's used for friction head loss and you backtrack that into the diameter from flow, you end up with a situation where the diameter, as you increase the diameter, your flow increases not linearly, it's more exponentially. It's if you do the math, it's 2.63 power to the diameter increase in flow. And so that's the reason why larger diameter pipes are much more beneficial in large flow situations, because if you parallel smaller pipes together, you end up with more frictional loss, more material, and you're going to have more pumping cost.
Yeah,
And so
that's hold on one second. That's a great point, Matt. You know, when you had me down last month, I mean, you were explaining that to me and the advantage. I mean, that is not to be understated. You know, Alan, we ought to start using that more and more in our large diameter presentations. But Matt, I just wanted to stop you 1 second and show the audience when I was there, Dan Landy and I saw this 63-inch DR11. You know, Matt, it was just 18 months ago that I was excited about 48-inch DR11. And you're now making 63-inch 11. That is huge. Engineers want that 200 PSI working pressure.
yes, and it's great for a lot of different reasons, not only for pressure, but it's also for structural, because as you start getting larger in pipe sizes, structural needs need to be considered as well. And so not only for pressure, but also for structural, and also for making fittings out of. If you're making segmented fittings out of these larger diameter pipes, you're taking basically sections of these pipes and you're mitering them in your welding operation to make fittings. And so there's usually a derating factor that goes into that. And so by having these much heavier wall pipes available, we can do elbows, segmented elbows out of this heavier wall pipe to then have the same pressure rating as the overall pipe system at a lower wall thickness pipe as well.
Well, thank you for explaining that. And just to my audience, we've gotten several emails saying that we're glitching. So Matt, let's you and I go camera off and just keep our audio on for the next 10 minutes or so and see how that works. All right. Thank you, Matt.
Great.
Back to you.
Okay, and so one of the things that we're able to do here at our Charleston facility is to make very long strings of pipe up to 2,000 feet in length, and we basically just extrude them directly into the river, and for ocean transport or transport up the coast. This process is we were able to do this because we cap the ends of the pipes so that they're buoyant in the water and float. And we can put a number of these strings together then, and then tow them to an application anywhere near shore to the coast. The process is basically very simple. It's basically the same operation as you're making short pipes. We're just not cutting the pipe. We're actually extruding it into these long lengths. We're ensuring the wall thickness by using ultrasonics to measure the wall thickness during the production of the pipe, and then counting the footage of the pipe to make sure that it is made to the correct lengths. And then we're able to extrusion weld and weld plates onto the pipe so that it can be buoyant and float into the water. And these pipes can be anywhere from 5 feet in diameter all the way up to 10.5 feet in diameter to be towed anywhere a job site has where it's near shore.
So, Matt, just to summarize for me here, Doug had shown us a slide earlier that said 36-inch DR9 could take 11 hours to cool time. So just the logistics of trying to fuse that 50-foot segment in the field, this innovation of your ability to extrude directly into a water body 2,000 feet up to 10-foot diameter could save a heck of a lot of time for fusion in the field. Is that correct?
Absolutely. And when you look at the freight cost savings as well, it actually is cheaper to tow than it is to go over the road. And we also have flanges on the end that we mount to. So when it gets to the job site, it's plug and play. You have flanges on each end of the pipe strings. And so you're able to connect these together, connect it back into your intake structure and into your intake onshore sump. And so it's a complete system that's ready to go once it gets to the job site.
Oh, awesome. I'm so continuing to be happy about the innovation that this industry does. So I'm not sure. Oh, I think that might have been your last slide for us, Matt. And thank you very much for your contribution. And Jeff Lohr, I believe, if you want to come on and take over and tell us why we are here. So there's a little bit of information on this slide to kind of sift through.
Absolutely. Thanks, Alan. So in the last 5 years, we've been engaged on a lot of potential opportunities for large diameter HDP, especially here in the Pacific Northwest where I'm based. And usually it's coming around the subject of aging infrastructure or connecting to legacy systems. So, one of the many reasons we're here today and why the demand for large HDP is growing is to touch on that. Like, we've got aging infrastructure that is reaching its shelf life and starting to see failure. And are we going to essentially replace that pipe with the same pipe we did before, either steel, or in this photo in the center, you see it's a reinforced concrete steel line pipe? Well, no, because HDP is now available in larger diameter sizes and higher pressure classes. So, we're seeing the request for it, the exploration for it, and we're getting more requests here, like I said, in the last 5 years than I think in my whole 19-year career. But other demand for the large diameter HDP is come from, again, it's the availability of steel from overseas. Hasn't been very consistent. So, there might be a push for large diameter HDP as a result. And longevity options, obviously, the design life for HDP at 100 years. Well, every year that we creep along here and add another life to existing HDP lines is more of a baseline model for people to explore it and design it so they know that it's actually hitting those 100-year lifespans. But it's a permanent solution that we're happy to support, and obviously sells itself in that department. But the following slides are exemplified of these markets that we're seeing the greatest potential for it. And I'm happy to say that these are projects that ISCO and myself has been involved with. But, the biggest opportunity that we see is obviously marine outfalls and intakes. No tuberculation, no growth on the pipe, a fully restrained system, no concern on joint breaking, and lots of quality QC to make sure that that's happening in each case. And then, Peter.
Question for you.
Yes, sir.
I did a little research on mussels and come to find out there are a lot of different types, Jeff.
Yeah.
You said there's no growth. I did hear that mussels can partially adhere, or at least one layer of them adheres, but that they're pretty easy to get off the inside of an intake or an outfall.
Yes. And then we're also looking at chlorination for those kind of situations, especially when it comes to, I think they're called razor mussels or something along those lines. But you're right, it can allow it, but it's very thin, but it does have a propensity for it not to allow growth in those cases.
And what is the procedure to remove them if they do adhere to the inside of HDPE?
It is a flushing. There's a pigging. There's also just a straight mechanical or raw, someone going down the inside of a pipe and removing it. But it's not consistent. It seems to be in patches, and usually it's adhering to something else to the pipe, the side of just the straight HDP.
Yeah, I've heard that a diver can just take his arm and sweep it on the inside of the ID of the pipe. And I also have heard the chlorination works pretty well. We don't have any official documentation on this, so there have been a couple of papers presented that I can share if someone is interested in that. Thank you, Jeff.
Yes. Next slide. The demand for large diameter in sewer force mains. We're seeing greater acceptance or exploration. This is another project on Vancouver Island in the city of Victoria, British Columbia. This was a 48-inch force main, and this is an in-ditch fusion weld being done by ISCO, just demonstrating the mechanical or non-mechanical options that could be used to join pipe if necessary, and you can maintain a fully restrained system when it comes to using HDP. And the next slide, the demand or the exploration for large diameter HDP in water mains, I'm pleased to see is growing. This is an active project, again, on Vancouver Island in the city of Nanaimo, where we had our P Alliance roadshow last year. And this is a 42-inch DR11 and 13.5 primary water line with a secondary line that's 30-inch. And as you can see, it's a textbook execution job, mainlining your pipe above and dropping it into the trench as such. So it's been a very good project. We're coming to the tail end of it, but I'd also like to highlight that all those fittings used were high pressure 200 psi HEP fittings as well, rather than transitioning to a steel in some cases. So ultimately, been a very successful project, but demand for water mains on HDP just makes sense. So potable water line is expensive water. Why would you want it to leak?
So, Jeff, I just want to circle back to something Matt Danish talked about, which was the friction factor. And oftentimes, comparing IDs, the theoretical single pipe, no appurtenances, no change in direction is what is used to compare material types. But I'll notice on the left here, we've got a significant amount of bends and fittings that otherwise have been avoided due to taking advantage of the allowable bending radius of HDPE pipe. So that should definitely be considered. And not only that, but it was a hell of a lot easier to work with in the field, I'm assuming, than putting a bunch of fittings in that natural curvature as well. So
that's
great picture. I'm glad you shared that with us.
Absolutely. And then the requests we're seeing, the opportunities are growing. We've seen a large uptick in demand for irrigation-based projects, canal enclosures. Again, HDP meeting those requirements on the diameter and flow rate, as opposed to our competitor products such as PVC or steel. HDP is being explored more aggressively in those avenues. The penstock transmission lines, we typically see on hydro projects that HDP is at the tail end of a steel line just for the lowest pressure systems, but larger diameter HDP has allowed it to essentially creep back further on those transmission lines and go with larger diameters that obviously have a marginally better flow rate or ultimately an easier install just because of a lightweight nature of HDP plastic. So, and HDP holds value. Again, here speaking to Pacific Northwest, the seismic consideration out here is a huge driver for installing HDP pipe, not just large diameter, but all diameters. So that consideration is a huge driver, as well as we've seen documented case around the world where those kind of instability in ground settlement or natural disasters, iconic photos of HDP being intact, not just water lines, but gas lines as well. On the high water table, again, we see HDP being looked at. Again, the non-corrosive nature of HDP, it's allowing it to function and obviously get a longer lasting pipeline. And then we speak to all the characteristics that we all know so well. It's lightweight construction, flexibility, again, great for low pressure systems that we can extrude with a weld joint. When I speak about low pressure systems on a fused joint, I'm talking about 50 PSI more. Yes, there are plastic options that are bell by spigot or jointed, which are fine for those less than 50 PSI connections. But again, solid wall HDP that's butt fused, low pressure systems is obviously something to be considered. And the demand or the request from us on the recyclability and the green element of HDP is being asked upon us more. And ultimately, HDP is a recyclable plastic. If it's a temporary line or ultimately you have excess pipe, there are companies that recycle and repurpose this plastic, new or used, considering the condition, and repurpose it into other plastic products. So, something to always kind of remind ourselves is that HDP is a recyclable plastic, and as all plastics are. And I like to say that, it's been a few years now, and knock on wood, but we've had a very steady supply chain on HDP. We haven't been tasked with force majeures or something like that. So we're seeing those kind of challenges face our competitors' products. So PVC, steel, an inconsistency on price and delivery. HDP has been holding steady in that front. And so it's obviously something to consider as well for your upcoming projects. And then with all pipelines, we need to be able to support that with fittings. And there are lots of available options out there for manufacturing of HDPE fittings, including ISCO, AGRU. But these are high pressure fittings that are being made in the factory or in the field, and giving us that flexibility to reinforce this as a fully pressure rated system and maintain those connections as a butt fuse joint, or in some cases transitioning to another steel, other pipe, legacy pipe. Here's a great example of AGRU's capabilities, some sweep bends or S bends. And again, AGRU provides wonderful bracing to maintain the shape at those joints so that it's an easier install, especially when we're dealing with thinner wall pipes. It just allows for more aligned fusing once the job starts, and make sure that that pipe's in shape. And there's a nice long sweep bend, again, custom bends. But on the right photo, I like this a lot just because of on the marine side. Consider not using stainless steel for your strainers or your intakes. There are HDPE options available, and they are intricate in detail. And as you can see, that's a great example of it. And you've gone the distance of designing an intake with HDPE, and then you transition to a steel. Let's maintain that system as a fully HDPE one, and AGRU creates a great product on this to maintain a whole HDPE system on that front. Again, we're dealing with a comparison of legacy systems on a regular basis. And this is a good example of the question of, well, can we ensure that HDPE, we can get an HDPE item that is equivalent to that of a legacy system. So I think this is a photo of a HDPE concrete manway of some sort, but we see its HDPE brother beside it, just ready to be installed.
So, Jeff, a lot of times in design of sewer systems or rehabilitation of existing sewer systems, the inlet and outlet elevations and flow lines and alignment of that manhole structure really need to be investigated beforehand, because that concrete manhole is precast off-site and then brought to the actual job installation. And then you're going to do the same thing, aren't you? Once you get the detailed elevations for flow lines, and once you get the detailed inlet and outlets, you're going to see that in these. Both are really just examples that with HDPE, you could do just about anything you want to.
Yeah, and Peter just corrected me, and this is also something to highlight, that the left photo is not concrete; it's just gray HDPE. So that is another consideration in HDPE, is that we are not limited to carbon black. We are able to color HDPE pipe accordingly, and that typically comes in with wanting to CCTV the line, essentially, or essentially making it a lighter on the inside if we needed to be inside and have some visual on that front. So again, we have the pipe, we have the fittings. Now we need the equipment to support it. I'm happy to say that the available equipment in North America to handle large diameter is growing. And these are all examples of large diameter machines available in North America to support that. For example, on the top right photo, that's a photograph of the McElroy Talon fusing the 1600 millimeter SDR21 HDPE pipe that was installed in Alaska for the Bradley Lake hydroelectric penstock line. So that was, needless to say, a unique opportunity, but as you can see, it mainlines the line from driving down the pipe and then grabbing it, pulling it up, and fusing it together. Currently 2 in North America. ISCO owns them both for your consideration, but at the same time, you look at the photo below that, it's the Weedos machine that was used on the McLaughlin Point outfall project. Again, for mainlining pipe, I would go with a unit kind of like that, especially when it comes to deployment underwater. But as you can see, multiple machines available to do or tailor to the kind of job that you're about to do. But McElroy's deployed their Trackstar units, again, for large diameter. Those have changed dramatically with the I series. Greater quality control, safety sensors, essentially a more user-friendly unit. It's kind of driving the market so that there's a propensity for people to take on those scopes as well if they want to elect to. So either way, a good demand for large diameter requires a healthy fleet to support it, and ISCO as well as others have that ability. And then just in turn with equipment, we need accessories. And I cannot stress rollers enough when it comes to large diameter. Rollers, rollers, rollers. Get as many as you can. It helps with handling. It handles with durability. It maintains shape. It's a necessary scope, and outside of your conventional butt fusing, where we only had about 2 pipe stands, the more the better. So McElroy again makes great products to support this. Poly horses, pipe stands, and pipe rollers, but look at heavy duty pipe stands as well for those higher weights. Is a consideration definitely when you're looking at DR11 north of 42 inch. You just need that extra support in terms of putting those into those fusion machines. And then ultimately, we've had these HDP systems, all great when it's brand new, but the reality is we're always transitioning into legacy systems like steel or concrete or PVC or stainless steel or things like that. And there are a lot of great options. A lot of companies have made strong innovation into creating restrained systems. And that is what we need on HDP. We need restrained couplings. It is a guiding principle in terms of the HDP product to make sure it is a restrained system as always. But again, great innovations being made by lots of companies like Robar, like Krauss here, doing transitions to HDP to other material pipes.
Well, hey, Jeff, great job. You're with A.H. McElroy out of Vancouver, and you're doing a great job. And I love working with you up in the Pacific Northwest in the provinces. You do a great job, and you have a wealth of knowledge. So thank you, Jeff Lohr.
Thanks for having me.
Alan, is it okay if I take these next few slides here before we go over to Dan?
Absolutely. I will. We've got about 21 minutes left, so make sure you do it quick. And before that, I'm going to take 30 seconds, maybe 20 seconds, Peter, to answer live one of the questions we've got. No, you could stay on, Pete. There's a question as to whether or not the industry is pursuing advanced resins to reduce the generation of microplastics. And I just want to come out straight away. There's a lot of development from the early 1000 series up to the 4710. Microplastics, the primary generation of microplastics as studied throughout the industry, has been through smaller throwaway single-use plastics. That's certainly the result of handling those single-use plastics isn't done that well. So Pete likes to say that the high-density polyethylene 4710 has just a single use, but it lasts well in excess of 100 years. So turn it right over to you now, Pete.
Yeah, it certainly is. My favorite single-use plastic is HDPE 4710. All right, we're going to go quickly through this so we can get to one of our stars here, Dan DeVia with Chen Moore. I love this project. Came out of Agru, where they did some 63-inch SDR26. Speaking of saving the day, this is a custom sewer job where they actually would drop one 20-foot segment of the polyethylene into the trench, fuse it, and move it down, keep moving it down. So this in Lima, Peru, helped save the day because tens of thousands of people had to deal with sewage in their homes as a result of a failing sewer line. They did not have the ability to do a bypass. So this was something Agru did very quickly on a super fast timeline, and hats off to our friends at Agru for this. And then going back to this project that Jeff Lohr did with A.H. McElroy up in ISCO AH up in Vancouver, the McLaughlin Point outfall line. This was a float and sink job where the fusions were done on this 2-meter diameter polyethylene pipe. They had the concrete collars put on them from a barge in the bay. Then they towed it to its install point and then sunk it in place so that they could connect up to the new outfall line for the wastewater treatment plant. So this was a 2.25 meter. So, and then 2,000 meters long, DR 21 and 26. We call that fuse and sink. Next slide, please. And then this is a project that I worked on with the city of Seattle. And then my colleague, Drew Mueller, who used to work for the Alliance, sold it at ISCO, where 60% of the water for the city of Seattle comes from the Tolt pipeline from that watershed. And we slip lined failing concrete with HDPE pipe. So we took advantage of the hose pipe. We used a relatively thin wall polyethylene pipe. Next slide, please. And we slip lined it. And it was 2,600 lineal feet, 66-inch concrete line, slip line with 54-inch polyethylene DR17. So that's like a 3.2-inch wall thickness or thereabouts. Very cool project. Happy that the city of Seattle is moving towards polyethylene. And Jeff Lohr talks about the seismic resistance. Oh my gosh, what a place that can use seismic. Then the biggest project that I know of, Jeff's colleagues from ISCO worked on this one, the Steinecker Service Canal enclosure. Yeah, we are now enclosing canals with HDPE pipe and seen tremendous benefits from no more evaporation or very little evaporation. These were agri lines. These were very large diameter. Go to the next slide. So 78-inch diameter. So this is 2-meter diameter polyethylene pipe put together with the Talon fusion machine and the Techno Dewey machine. And look at on the upper right, the polyethylene being just bent around these sections of open trench for a canal enclosure. Very cool project. Happy to be part of that. What little we could do to educate people about polyethylene, but great job, Agru and ISCO, with that huge job. Now I'd like to introduce Dan Davia with Chen Moore. Welcome to the show, Dan. I'm so delighted to finally have met you and have you be part of this program, because you've got some pretty cool stuff to talk about here in Fort Lauderdale.
Thank you, Peter. Very happy to be here today. Good afternoon, everybody. And I'm excited to be part of the group, really. So I'm with Chen Moore. I'll give you a little bit of background. Chen Moore, we're doing engineering for 24 years now. And we're located here in Fort Lauderdale. We're a consulting engineering firm. And personally, myself, I've been involved with large diameter pipeline for 15 years now, whether it's pressure pipe, water, sewer, reclaimed water, raw water, as well as drainage pipeline. So you heard so far about the HDPE evolution, the resin evolution, its properties, the fabrication, and its durability. But I'm here to give you the engineer's perspective as to what I see when I'm designing or I'm in the field during the construction of pipeline, the benefit of large diameter HDPE pipeline. Really, I see the benefits clearly into two distinct categories: the performance benefits and the design and construction benefits. The performance benefits is really how the pipe behave. A lot of it you've already seen during the course of the presentation, but this pipe is corrosion resistant, is resistant to hydrogen sulfide, abrasion resistant, has a smooth internal surface, the smoothest surface that I know of for pipelines, and excellent surge pressure tolerance. And as it relates to the benefits during construction and design, this is considered jointless pipe. So that's a restrained pipe. I'll talk about it in a minute. It has incredible trenchless versatility, HDD, horizontal directional drilling. Peter just talked about slip lining. There's also close compression fit lining. Some people know it as swage lining. And pipe bursting is going up in size as well. And custom-made fittings, we spoke about that. I'll touch on it a little bit more and how we implemented this in our project. And the availability on lawn segments. Next slide, please. So let's talk about those performance benefits. This pipeline is resistant to hydrogen sulfide. Hydrogen sulfide is a gas generated by sewage. So it's very prevalent and present in sewage force main pipelines and usually stays at the top. So essentially on metallic pipes, what you will see is failure at the top, as you see on the picture to the right? And these are things that are avoided by using HDPE pipe because it's inert when doesn't interact with hydrogen sulfide. Similarly, corrosion resistant, especially when you're working near the coastline, brackish water or high salinity. We don't have to worry about with HDPE being resistant. Next slide. Another benefit of using this pipe is that all pipes, whether it's gravity or pressure pipe, has some sediments. And then with sediments, there's a scouring at the bottom, and there's eventually loss of material. As you will see on the picture, this pipe failed at the bottom. So this also is a benefit of the HDP latest resins. Let's talk about water hammer or pressure surges. There's great tolerance because HDP is flexible, and everybody has experienced water hammer is when you're in an old building, maybe in a hotel, you shut down the faucet too quick and you hear the bang on the walls. That's essentially the water being stopped instantaneously, and it hasn't dissipated the energy. So the energy needs to go somewhere. It's usually absorbed by the pipeline. Because HDP is flexible as opposed to being rigid, it has the capability of absorbing this. So quickly, that table from PPI, Plastic Pipe Institute, PC meaning your pressure class. For occasional surges, you can withstand up to 2 times the pressure class. And for recurring surges, you can withstand 1.5 times the pressure class. So quickly on the right, you'll see a little exercise. HDP DR11 200 is rated for 200 PSI, which means the recurring pressure is 300 PSI and occasional surge is 400 PSI. And you may say, okay, Dan, that's not a whole lot. That's another 100 PSI on each one. But if you focus at the very bottom, you'll see metallic pipe, such as ductile iron pipe, with a change in velocity of only 2 feet per second. When you change that velocity, it will experience a pressure surge of 100 PSI, as opposed to HDPE, because the flexibility of the pipe will absorb the energy for that same change in pressure is only just about 20 PSI. So HDPE pipe essentially, what this means is it experiences less surges and less pressure during the operation of the pipe. Next, please. And the last thing I want to talk about, the benefits of the performance of the pipe. It comes in 50-foot segments as opposed to maybe 20-foot, and some pipes, such as concrete, come in 8-foot segments. This means less joints and less opportunity for leaks. Next, please. All right, on to the project on the real. How do we use all these benefits? Now, I figured before I'll give you a little background about Fort Lauderdale. This project was in the city of Fort Lauderdale, the 54, 48-inch emergency redundant force main. And I wanted to show you these aerial views because Fort Lauderdale, really, most people don't realize, it's called the Venice of America and has 165 miles of waterways. It's connected to the Everglades to the west and to the east to the beautiful Atlantic Ocean. Next, please. So just about Christmas time in 2019, in February 2020, the city of Fort Lauderdale experienced a series of catastrophic breaks. It was unfortunate. This was the main transmission line, a 54-inch line going into the wastewater treatment facility. The picture to the left is actually one of the breaks. This was due to corrosion as well as scouring at the bottom, abrasion. Next. The result of this was 211 million gallons of sewage that were spilled into the waterways and the canals. Those pictures, as you can see, that's a boat dock. And it was all over the news. They got it wrong. It says water main in there, but it's really sewage flow. And remember those aerial views with 165 miles of canals. In Fort Lauderdale, we have manatees, we have dolphins. I mean, these are pristine waters. So you get the picture of what occurred here. Next slide, please. Just to give you a better flavor of what occurred, sewage all over the place, several feet high. And the result of this, next slide, please. There was an emergency call from the city manager, 10 a.m. in the morning, right before Christmas Eve. And within a few hours, by 4 p.m., the program manager at the time, still is Hazen Sawyer, they put out a progressive design criteria package. A few firms were invited that were capable of performing this job. And the goal was to install the fastest pipe ever to be installed in the city of Fort Lauderdale. Next. 2 teams were selected. The Murphy Pipeline team and the DMSI, David Mancini team. I'm sure a lot of you in this call know these very reputable firms, very capable. The project was divided in 2 sections, north and south, although all the consultants and the contractors, the 2 contractors here, we worked as a team. And the goal was to build 38,000 linear feet of large diameter pipeline within 18 months. Little synopsis. This was done through highly urbanized areas going through the heart of downtown Fort Lauderdale. Buildings, schools, you name it, 38,000 linear feet of pipe, 17 total horizontal directional drills, ended up being 91% trenchless, 3 subaqueous crossings. There were environmental sensitive areas, as I mentioned, limited right-of-way in some instances going through DOT road and county roadways. And of course, to top it off, built through the COVID pandemic. Wanted to show you quickly the phases. Once we got the NTP, the team quickly realized that in order to expedite this project, we needed to have several phases. All in all, at any given point, you had several crews, and you can have multiple phases under construction, multiple phases at the same time being designed while others were being permitted, and perhaps one phase was being tested, getting ready for certification. Next. The one thing that we did as soon as we got together with the team was the selection of the material pipe. And we knew this was a fast track project, difficult conditions, large, congested corridors. And so what we just decided quickly is we needed HDPE pipe. And there are several reasons for this selection. First is corrosive environment, high salinity near the intercoastal. Second, the reason for this pipe failing, the original pipe, was scouring, abrasion resistance. So we knew this. We needed to have a pipe that will mitigate this. Then we needed the ability to manufacture custom-made fittings on site. Why? Because we're dealing with pipe that is almost 5 feet in diameter. And when you're thinking about a fully developed downtown area, is full of utilities in a narrow corridor, and we have to be able to maneuver. One bullet point I don't have here is we wanted to do trenchless to mitigate the impact to the community. And because in some instances, trenchless, it could be much quicker than open cut. Then we consider this pipe to be jointless, and it needed to be restrained. I'll speak to that in a minute, but I want to focus on the last bullet in blue. It allows us for less clearance from other utilities. This is from the Department of Environmental Protection. Most engineers and contractors know that you need to stay from water main 10 feet in separation. This is a requirement. Sometimes it will allow you to go as close as 6 feet. There's only two conditions, two variances to this situation. You encase your pipeline, then you can get close to it. And if you don't encase your pipeline, you have to use a jointless pipeline. So HDPE is jointless, and we can put this pipeline next to a water main and we'll get approved. In fact, this is our third project doing this. Whenever in need, we use HDPE because it's jointless. Next. This is a quick picture of, or aerial view of the fusing and laydown. As I mentioned, there were DOT 6-lane divided roadways, but there were also narrow stretches of residential areas. And this is a setup with a fusing machine and the staging. Next. So let's talk about fully restrained. What you see here, this is an aerial picture. Actually, I took this picture myself. When you're using pipes that use the bell and spigot methodology, and depending on elbows and T's and deflections and that sort of stuff, it needs to be restrained. It's a requirement. And one way of restraining is it could be incorporated into it, but a lot of times you need mechanical restraints. And so most other pipes come in 20-foot segments. Then you're going to be needing this type of what you see on the right, mechanical restraint every 20 feet. HDPE pipe is basically fused. Think about like any other welding, doesn't need to be restrained. So this is think about a hose in steroids. So it was tremendous savings on material as well as incorporating speed in the overall performance of the project. Next, please. Quickly, just to show you, one of the crossings, a 60-foot depth. We have to permit through the U.S. Army Corps of Engineers. Is this crossing the intercoastal? Next. And then we talked about custom-made fittings. This was incredibly helpful for us from an engineering and construction perspective. Again, we were fast-tracking this project. We went to the field. We didn't have sometimes the opportunity to do a thorough investigation. And in any normal utility on a congested city, you will encounter water, sewer, drainage, fiber optic, duct banks, all kinds of utilities, gas lines. and we have to be able to maneuver. So what custom-made fittings afford us to do is to be able to maneuver around, take measurements, and miss all these utilities, as opposed to your standard 45s, 22.5s, or 90-degree mending. It would have simply just not been possible with large diameter pipeline. Next. Really, I think this is my favorite picture to the left. This was all fabricated outside, and really the background story on this is one of our subaqueous crossings. We couldn't do it with horizontal directional drilling, didn't have enough spacing, couldn't do it also for with microtunneling or jack and bore. There was just too congested. There were these nice neighborhoods and mansions on both sides of the canal. And to top it off, really the streets on each side of the canal, the right-of-way did not align with each other. So they were almost like staggered or offset. So we had to take measurements and build this piece that you see to the left above ground to be able to fit it in. And then eventually at night, it was sunk in by attaching concrete poles as ballast, as you can see. And once it was sunk in, we put concrete slabs on top. Once secured, then we were able to connect on both sides of the canal the rest of the pipe. Next. So I know I went through a lot and quickly, and everybody went through this presentation with all the benefits, but what you see here, all these items on the right, it just highlights all the benefits that we went through, right? Pipe is corrosion resistant. This project needed it. We also, being this a force main, we needed to be hydrosulfide resistant, abrasion resistant, had a smooth surface for added flow, great for surge pressure tolerance. It was jointless, so fully restrained, as you saw on all these slides. Trenchless, 91%, and of course, custom-made fittings. It is my opinion, really, that for the speed of a project like this, certainly we selected the right material, and it was a successful project and has been featured in many magazines and won several awards. Thanks again.
Dan, you're an absolute rock star with that. Thank you so much. It was really summarizing everything that we've said to date about the innovation with it. Also, I'd like to go back to this picture in particular, because we get a lot of questions about hoop strength, and that's the modulus of elasticity that is so much lower than, say, a ductile iron pipe. Obviously, a rigid modulus of elasticity would not give you the ability to ease of workability that is inherent to this material, which you recognized up front. And a lot of the hoop strength, as you've shown through calculation of surge, is really overkill when we look at surges through that pipe itself. So in these really just prove all of those points in itself by showing the proof is in the pudding in the pictures. So thank you so very much for showing that to us and recognizing that HDPE would save the day, as Pete likes to say, and absolutely did in this scenario. So now stay on, everybody. We've only got 30 seconds left. If we had any other last minute comments, Peter, you got it?
Yeah, great job, Dan Devia, Doug Keller, wonderful job, Jeff Lohr with ISCO AH, Matt Danish with Agru America down there in Charleston. Fantastic show today. This will be up on YouTube, guys, in the next 2 days. Take a snapshot of that if you want to get a hold of any of our speakers today. And for that, my name is Peter Dyke. This is Alan Ambler. And right now we're signing off and we're saying thank you for tuning in to this edition of the Alliance's webinar program on Big Pipe. Till next time, join us next week when we're going to talk about PE inspection.